Okay, welcome everyone to the workshop of Stage 3. So today with us we have Carolina from Siemens. So she comes from a background of biomedical engineering with specialization in neuroscience and experience in investigating predictors of neurological disease. But now she's a data science at Siemens at Analytic Labs, and she works she works in the business units to help create data-driven solutions in problems in such fields as mobility, finance, and automation. If you want to catch her a bit after the workshop and want to have a common topic, then I'm pretty sure you can talk to her about traveling, video games, and anime. Hi, Carolina. Welcome. How are you?
Hello, I'm fine, and you?
Good, good, good. I'm enjoying this really weird, good weather in Belgium, so that's nice.
Awesome. Here it's good as well. Yeah, it's sunny at least. Thank you so much
Perfect.
for introducing me. And do you want me to? Can I start?
Yeah, just maybe before just maybe one quick question. Could you perhaps like tell us in one sentence what is going to be the main topic of this workshop?
Okay, so at Siemens, I've been involved in a couple of computer vision projects that revolve around traffic analysis of videos. So that will be like the main focus of this workshop. And I'll also be walking you through some of the challenges that I face, some of the lessons that I've learned, and I'm hoping that someone can find them useful and insightful for their own projects in the future in this field.
Perfect, perfect. Well, I think this is going to be very useful for the also for the participants, since one of the challenges it's exactly computer vision. So let's
Okay.
see. Good luck, Carolina, and thank you so much for bringing this workshop to our participants. See you in a bit.
Thank you. Thank you. I'll start sharing. Okay. Okay. So as I mentioned, I've been working in these two computer vision applications regarding like traffic analysis of videos. And after this presentation, I've also prepared this Jupyter notebook that I think was already shared with you, where we'll perform also some tasks that I'll be going through in this presentation. So let's begin. And I'm going to start just with this small introduction about my team, like to give you a bit of context on how these projects came to be. And well, in my team, which is the analytics lab at Siemens, we use machine learning, artificial intelligence, and also data analytics methods to drive digitalization. And in our projects, we are involved basically in every step of the way. So from idea generation to developing that initial proof of concept, like to see if those ideas actually work, until we eventually get to this fully working application. Another cool thing about our work is that we can develop these projects for any Siemens division, like smart infrastructures, mobility, health and years, meaning that we can work on very different topics and it never really gets boring. So we are this international team, and besides Portugal, we also have colleagues in Germany, in China, and also in India. And we all come from these very diverse backgrounds, both academically as professionally. So as these projects that we develop can be done for different departments within Siemens, they can also cover different data science topics in the end. Here I have some examples of these projects that we've done within the team. And I can tell you that like the most usual topics are prediction, like forecasting some monthly revenue for a certain division, and also like text analytics, so sentiment analysis of like tickets that have been submitted to a Siemens platform, for example. But today I'll be focusing on two of our computer vision topics, so Traffic Airnalytics and 5G Mobics, and let's dive into it. So imagine that there's this intersection like the one that you see here in this video in your city. And it has a lot of traffic jams, in rush hour you can hardly move in there. And the city hall decides that they want to do something about it. They want to fix it. So they need to commission a study to find the best possible traffic solution for this intersection. And this could be something like adding a traffic sign or some traffic lights over here, or even maybe like an intersection isn't the best solution. Maybe the road configuration should be like a roundabout, stuff like that. So the first step in a study like this is to get information about traffic flow. And that usually means that you get a video like this, acquired from a static traffic camera. And then some poor souls will have to look at hours of this video and basically count the number and classes of vehicles that go through each one of these routes. Like one car enters through entry 1 and exited through exit 3, or entry 2, exit 2. And then in the end, they have to fill up these huge Excel sheets with all of this information. So with Traffic Airnalytics, the goal is basically to improve this very boring and in the end also expensive approach. So firstly, what we do is we use a camera mounted on a drone to acquire the footage. And we get images like the one that you see here. And this gives us a lot of advantages. Why? Because we have less obstructions between the camera and the vehicles, while like in a static camera like before, if you have like a larger vehicle closer to the camera, it can obstruct other vehicles behind it, for example. And here we don't have that problem. We can cover a wider area. You basically just need to increase the altitude of the drone. And it's also a flexible approach because we can take the drone basically anywhere. Although, of course, you need the required permits to acquire footage like this. Then we apply some deep learning and video analytics to both detect the vehicles and also track their routes throughout the video. So in this project, there are two main challenges: the detection of the different classes of the vehicles and then the tracking. So let's start with the detection part. So if I show you a picture like this and I ask you what do you see here, I think we can all easily say that it's a cat. But then if I show you this one, I mean, by looking at it, like from a logical standpoint, it's really very different than the first one, right? I mean, the position is different, the background is different, everything. But we are still able to identify it as a cat. How do we do that? Probably because throughout our lives we have seen many images of cats, or maybe like some cat videos on YouTube, or we might even, have a cat or have interacted with cats in the past. So we've basically been exposed to cats from different angles. Also, we've seen cats from different breeds with different colors, and we learned what characteristics make up a cat. But how do we teach this to a machine? From a programmer's point of view, the most immediate answer would be to define like a set of rules or instructions. So imagine if the object has pointy ears, slitted pupils, whiskers, fur, some cute paws, and a long tail, then we have a cat. But is this enough? There are many different kinds of cats. Some of them don't even have fur, some don't have tails, others have a lot of fur. They can have different colors and shapes. So in the end, you would actually need an infinite amount of rules in order to define what characteristics and features make up a cat. And obviously, this is impossible and it can't be done this way. So what we do is we teach the machine by using examples. And if you want a machine to be able to identify cats regardless of their background, their color, their breed, or the perspective, we need to feed as many different images as we can. And then we let it learn by itself what are the most relevant features for classification. So these machines that I'm talking about are actually deep learning algorithms called neural networks. And neural networks basically try to mimic the way that our visual system works. And that is why they need to be taught, like we were, sort of, by using all of those examples that I mentioned. Neural networks are comprised by different layers, like you see here in this schematic. And as these labeled photos pass through the different layers of the neural network, they undergo a series of computations, and then features of those images get extracted. So here I have another example where we are trying to detect faces. So our examples look like this. And you can see that as we go through the different layers of the neural network, different kinds of features get detected. So in the initial layers, we see some low-level features. As you can see here, they are very simple, very basic, like lines and edges and some blobs here. And these features are actually common to every image in all of those different categories that we have. But as we move on through the neural network, as we go deeper, we start seeing some medium-level features here. And as you can see, these are actually like different combinations of the generic features that we had before. So basically, you are starting to see here some actual object parts, even though the algorithm wasn't really taught to look for them, which is kind of amazing. So you actually start to see here some noses, some eyes, some things that resemble a mouth. Um, and it's really interesting that neural networks can learn these higher level representations themselves by deducing them from that training data that we feed to it. And the deeper you go, the more sophisticated patterns you get. And as this iterative learning process continues, and as different images go through this neural network, the weights and the importance of these features get updated. And in the end, the neural network basically learns this set of rules or weights that will help it identify the target class in the end. So then, when we give like a new picture that the neural network was never exposed to before, it will extract those features, apply those previously learned weights and rules, and it will be able to output if the target class is there or not. So in this case, if it is a cat. So far in these examples that I've been showing you, I focused on this classification problem, where we're just basically interested in checking if the target class is present in that particular picture, like if there is a cat or if there is a face in there. But there are other more complex computer vision problems that can also be solved with deep learning. So if you want to know where the object is in the picture, then you have a localization problem. If you're dealing with multiple objects, then it's an object detection problem. And if you're interested in the fine edges of each individual object, then we are dealing with an instance segmentation problem. So as you can imagine, in these projects that I'm sharing with you today, our first challenge is called object detection, since we want to both identify but also localize each object. But unfortunately, instead of dealing with these cute cats and dogs and ducks, we have 5 target classes. We have buses, cars, trucks, pedestrians, and two-wheeled vehicles. So object detection has seen a lot of growth in recent years due to the evolution of deep learning. Before deep learning, you could do object detection by basically screening an image using sliding windows of varying sizes, trying to find predetermined features of the target object. But as you can imagine, this was very slow and very computationally expensive. But in 2013, with the advancements in the field of convolutional neural networks, we started really seeing some big progress in this field. So these initial CNNs that you see here, so our CNN family of detectors, are all region-based. So in this, the detection actually happens in two stages. So first, the model proposes a set of regions of interest, and then a classifier only processes those candidate regions, and it tells us if the object is there or not. And although this is a smarter approach than using a sliding window, because in the end, with a sliding window, you are considering like an almost infinite amount of regions. These methods end up being still kind of slow, even though they achieve high accuracy rates. Then, with the appearance of YOLO and SSD, which are one-stage detectors back in 2015, basically this performance saw quite a big improvement, basically. In these detectors, they basically skip that region proposal stage, and the detection is run directly over the whole image. They consider this dense sampling of possible object locations, and they generate both the bounding box coordinates and also the class probabilities. This ends up being like a much simpler and faster approach to object detection at like a small accuracy cost. And you can see here that both the RCNN and the YOLO detectors have seen some iterations over the years, and each new iteration usually means that it has a performance and accuracy improvement overall. So just to give you like a more in-depth analysis of each one of these types of detectors, I will start with the regional convolutional neural network, or RCNN. So in this case, we have our input image, and first we apply this selective search algorithm. Basically, what this algorithm does is it applies image segmentation and then combines regions that are similar to each other based on stuff like color, texture, size, and shape. And in the end, it groups them together into this larger region proposal. So for each image, you will get about 2,000 region proposals. Then each one of these regions gets reshaped or warped into the size of the input layer of the CNN, which is usually a square, like you see here. And then the CNN extracts the features from each region proposal. And finally, we apply this binary SVM to the resulting feature vectors of these regions. And we are basically classifying if the object is there or not, or if we are dealing with a background. So this is basically how the RCNN works. But now let's look into YOLO. YOLO actually stands for you only look once. It doesn't mean you only live once, at least in this case. And it's an example of a single stage detector, like I mentioned before. So we are basically looking at the whole image at once. So first, we apply this S by S grid on our input image. And then each of these cells will be responsible for predicting n bounding box and probabilities. In the case of YOLO v4, for example, so that latest version of YOLO that I talked about, each cell predicts 9 bounding boxes of different dimensions. So in the end, we end up with this very dense set of possible bounding boxes, all of this mess that you see here. But most of these bounding boxes will have a very low probability of having an object within them. So we basically have to clean this mess up. And the first step here is to basically delete the boxes that have a very low confidence of having an object within them. And we do this, sorry, we do this cleanup by using the intersection over union. And when I'm talking about confidence, that is actually what I mean. And this IOU is basically the overlap between our prediction, so this purple box over here, and our ground truth. So it is the intersection between both these boxes over the union of both these boxes. So the yellow over the green area that you see here in this example. So if we apply a threshold, which is usually, and what I've been using is around 50%, you end up excluding all of those meaningless bounding boxes or possible bounding boxes that we have. But you still get a lot of like overlap in the bounding boxes that have a high confidence, like you see here. So we have multiple boxes around the face, but it still needs another layer of cleaning here. So what we do in this case is we apply what we call the non-maxima suppression. And we finally identify what is the optimal bounding box among all of the candidates here. And in the end, the output will be just one bounding box per object as we intended. So for our smart traffic projects that I've brought today to talk to you about, the neural network that we chose to use is actually YOLO V4 because it has some great performance overall. So if you have an object detection task, a typical approach would be to download some pre-trained weights of YOLO V4 or any other neural network that you want to use that has been previously trained on some huge imaging dataset. Here I have the example of the COCO dataset, which has like hundreds of thousands of images, and they have all been labeled for 80 different classes of objects. This means that passing an image like this, like the one that you see here, through that already trained model, you get these results, where almost every single object in that picture gets labeled. You know, the cars, the bicycle, the person, even the traffic light gets identified. However, if we try to do the same with our drone-acquired images, nothing gets detected. And why? Because these huge datasets like COCO are all made of images that have been acquired at an eye-level perspective, like the photos that you could take with your smartphone. So this approach doesn't really work for aerial perspective images. And why? So besides the fact that we're dealing with this bird eye view, there are some other issues with these aerial images that turns this problem into something a little bit more complex. So we have also some very small objects in the scope of the whole image. Each vehicle occupies just a small percentage of the image. The scale can vary depending, as you can see in these examples, on the altitude of the drone that is acquiring these images. We can also have multi-directional objects, particularly when we're dealing with these roundabouts. Obviously, one vehicle can have multiple rotations, but it will still be a vehicle, right? And we also can have different background complexity because we're covering a wide area. So our solution to this problem was to actually train YOLO V4 on a custom dataset comprised by aerial images where our 5 target classes were labeled. So let me just drink a bit of water. So in the beginning, I first decided to explore what datasets I could find online that had this type of aerial images and that were labeled for the classes that I wanted, right, for vehicles. And I found some options. So one of them was called this DOTA dataset that had some very large images and was acquired at a high altitude. But it would require major pre-processing. These images were really very large, and I ended up just dropping it, not using it. Then the VDI dataset, and here I actually learned a quite important lesson that I wanted to share with you, because since YOLO looks at the whole image, it's also a bit sensitive to context or to the type of background that you might have in your training images. So in this case, with the VDI dataset, we had a lot of these rural context images, So when I then tried to use this train model on my urban images, it didn't work out well. It didn't generalize well to like an urban environment. So in the end, I actually found a couple of data sets that had this urban context that I learned was important as well. Um, they have multiple images. It required quite a lot of pre-processing and validation, but in the end, I ended up with some decent initial results. But instead of scouring the internet for that perfect dataset that might not exist, and in case you have your own imaging dataset that unfortunately is unlabeled, you kind of have two options here, right? So you can either label it yourself or have someone else do it. So when thinking about labeling it yourself, you really need to ask the question, is it worth it? And is it doable? So usually in these types of data sets for computer vision problems, you need thousands of images. So it can really be a pain to have to label every image yourself. And it gets worse when you are dealing with like multiple classes or images that have many, many objects at once. But well, if in the end you feel that this is the right solution to you, there are some tools that you can use like label image and open labeling, among others. I think these are actually Python based, so that's why I put them here. So you can use this to make the job easier. But if you feel that it's best to have someone else do it, you can also have some different options here. They are based on crowdsourcing. So you can outsource that crowdsourcing to services like Amazon Mechanical Turk or Scale AI or Appen, just to name a few, where basically you pay for each image and or object that you want to identify in your dataset. And there's this distributed workforce around the world, possibly, um, where those people are basically paid to label the data for you. And another option is basically in-house crowdsourcing. So you are trying to get that workforce, but from within your own company. So actually, in this project, this was something that we tried, so this last option. We had some test videos that were acquired at different altitudes and times, like the one that you see here. So what we did is we first ran our object detection model that was trained on those two datasets that I showed before. And you can see here, like this frame here, you can see the results that we got. So a lot of the cars got identified, yes, but there were still some missing labels over here. So what we decided to do was to launch this internal contest here at Siemens Portugal, where we gave a drone as the first prize to the person that would correct the most images possible. So what I did was I created an executable based on Python and OpenCV that read the labels that were already there, which are here in blue, and then asked the user to basically correct what labels, whichever labels were missing, or also if there was an incorrect like classification here. So instead of a car, you'd have a truck. The participants could also make that correction. So let me just show you here what the participants had to do. So as you can see, they basically had to draw the labels around the missing the vehicles that have missing labels using obviously the appropriate label or class here. So in the end, this contest was actually a good success, and we were able to actually get a very decent data set from it. Now, an additional note regarding these labeling processes and how this all works in the end. So here is basically a sample of how the dataset for training YOLO looks like. So you have your JPEG files and your text files. The JPEGs, as you can see, is just the image. It doesn't have any labels or like those rectangles around them, around the vehicles. All of those label information is actually on the text file. as you see here on the right. So basically, this format, this YOLO format, looks like this. So it starts with the object class. So it's a numeric between 0 and the total number of classes that you're dealing with. In this case, we had car, truck, and bus, so 0, 1, and 2. Also, each one of these lines actually represents one of the detected objects. So we have 5 objects here, or vehicles. And we have 5 lines here on the text file. Then we have the centroid coordinates, and also the width and height of the bounding box. The centroid is the center of the bounding box, like you see here. And all of these values, you can see they are between 0 and 1 because they have been normalized to the size of the image. Then there are also other annotation formats that you can come across, like the COCO. So instead of using the centroid and width and height, they can use other coordinates for the bounding boxes, like the top left corner and the bottom right corner. And for example, like if you want to perform some validation, like you see here, where you see the rectangles around the vehicles, you will also need to use the OpenCV draw rectangle function, which uses the top left corner and bottom right corner in order to draw these rectangles here. So what I mean with all of this information and what I wanted to tell you is that it's important that you are able to easily or to design some functions that can go from one of these formats to the other and vice versa, because you can also find different training sets, data sets on the internet that can have different formats. So you need to be able to interchangeably use either one or the other annotation formats. So in our project, we had eventually this new requirement where we had to expand the classes that we were initially considering, which were just car, bus, and truck, to also include pedestrians and two-wheeled vehicles. And to do this, we had to find a new dataset that had all of those classes labeled. So I found this Visron 2019 dataset, which had labels for all of these classes and more. So first of all, I had to basically select the images that had this top-down view that you see here, because in this dataset there were also some other images that were acquired at an angle. Then I first had to remove all the images that have ignored regions. So basically these were regions within the image that even if there was an object within them, it wouldn't be labeled. And why? And this is very important as well for you and for other projects. For training YOLO, you need to make sure that every object, YOLO and other CNNs, for object detection, you need to make sure that every object that you're trying to identify is labeled in the training set. Because otherwise, YOLO will learn that the characteristics of that object are actually part of the background, and you will see your performance drop. So I first had to remove all of those images that had ignored regions. And then I also decided to merge some of these different classes that I had in this data set, because I wasn't really interested into having this level of detail or differentiation between them. So the classes that I ended up with were the pedestrian, two-wheeled, car, truck, and bus. This is also a type of pre-processing that you can face in your projects. Having to merge different classes, even, I don't know, due to your project specificities, or even to just simplify the training, because with additional classes, it means that you'll have to have more images and more training time in the end for the model to be able to deal with all of this. Here I just have an example of the labeled dataset in the end. This is actually like a cropped image of that, but you can see all of these different classes here that I used to train the model afterwards. So I now have a problem, right? I have a new problem, because in the initial dataset that I was using, that came from that contest that I mentioned before, I had three classes, car, truck, and bus. And in the new dataset, I have those 3 classes and 2 additional ones. So how should I move on with this data? So when you're facing a problem like this, you have 3 possible solutions. One is to retrain the model from scratch with images with all classes labeled in every image. And this means that you have to make sure that in the whole dataset that has less classes, there were no occurrences of the new classes, because they would have a missing label. Of course, they weren't labeled for those classes. Because, as I mentioned, every single class needs to be labeled in every image, or else the detection performance will drop. Then the second option is to train a different model to only detect your new classes. And then in the detection or tracking stage of your project, you would apply both models. So this is called model stacking, and it can be a good approach, although it's another layer of complexity because you're basically using 2 models instead of 1. But in this particular case, since my new dataset also had the old classes, it actually felt like a waste to not use them. Like I could remove these classes and just consider the new ones and then do this. But it would feel like a waste, so I didn't do that. And also, like if I decided to train one model in the first dataset and another model in the second, then how would I handle those overlapping detections? It wouldn't be like an easy call, so I dropped this option. And then the third option would be to apply transfer learning based on the previously trained model, so the one trained in the contest dataset. So as I mentioned in the beginning of this presentation, the initial layers of the neural network cover some low-level features like the edges, the shapes, the corners, meaning that that knowledge can be reused for similar tasks. You can basically freeze some initial layers of the neural network and just train the deeper layers using a new data set, like you see here. So you can basically leverage that knowledge that you get from the first learned task and reuse it for this new task. In this case, the identification of two new classes. This is actually a very interesting topic. There has been some recent developments in this field and around transfer learning. There are some good papers out there, so feel free to look it up. And it's really a very compelling option when you are facing a decision like the one that I faced here. But in my case, actually, around the time when I faced this issue, it was just after YOLO v4 came out, so last year, before I was using YOLO v3. So I was already going to have to retrain the model using this new network configuration. So I went with option 1, which means that I had to basically exclude a lot of images that I had here in the first dataset that had the pedestrian and two-wheeled classes that weren't labeled. So it required a lot of work and validation, but in the end, it worked out okay. So after you have like your dataset almost ready to go, another thing that you can try is to improve it. There are some things that you can do, like adding negative examples, which is actually quite important for YOLO because, as I mentioned, it also learns what the background is. And basically, a negative example is an image where you don't have any objects. So it's empty, and the label text file is empty. So you should also have as many images as possible with negative examples so that the model can learn what is not an object, basically. Another thing that you can do is data augmentation. So when you perform data augmentation, you're basically taking an image and then applying some modifications to it in order to create multiple new images to increase the size of your data set. So here, for example, you can apply some different transformations to the image, like messing around with the sharpness, the blur, the colors like black and white, or you can also retrieve like the color channels like red, green, blue, or adjust like the saturation of the image. And all these transformations are, you are basically keeping the same dimensions and orientation of the original image. But then you can also do other types of modifications that mess around with the dimension and orientation, which can be rotations, like you see here, or also cropping parts of the pictures. And I wanted to uh, pull your attention towards this, because if you perform this type of data augmentation in an image that has labels, uh, when you perform this type of alterations, then you'll also have to adjust the labels, because as I mentioned before, and you saw the example that I showed you, the labels for YOLO also are normalized to the size of the image, and the centroid position would also change with this type of transformations. And of course, well, if you're dealing with a negative example, then you don't have this problem. You can pretty much do any type of transformation without worrying about the labels, because it doesn't have any. So here I have summed up some of these cleaning stages that I had to go through uh, while treating the data sets. So the first one, data set merging and filtering. So merging the data sets that you want to use, and also filter out any type of images that you are really interested in. If you have like a flag for it, I was lucky enough that the data sets that I used had that type of information. Then you can also adjust the labels and perform some validation of your training set. So adjust the target labels, like, you know, if you're only interested in like a subset of them, or like I showed you before, like merging those multiple different labels into a single one. And in the end, you should also validate if every object is labeled correctly in the data set. Then you might also need to convert annotations. So depending on your model and the dataset that you want to use, you might need to convert the annotations between all of those different formats that I showed you before. And if you want to perform those validations with OpenCV, with the rectangles drawn around the objects, you also have to do this. Then you can enrich the dataset by applying either data augmentation techniques and also adding, for example, negative examples. And in the end, you should perform this final validation. So you need to check, and check again. Because in the end, bad training data means bad detection outcomes. So yes, it isn't fun to go through like thousands of images, making sure that they are okay. But yeah, in the end, the results can really depend on it. So yeah, my recommendation to you is to always validate your data. So in the end, we were able to basically train YOLO v4 on this new custom dataset, and we were able to get results like this, where our 5 target classes got identified. So just a final note on this training and detection part regarding cloud services. So here I'm actually talking about the Amazon Web Services, so AWS Cloud. But this is obviously also applicable to other cloud services like Microsoft Azure or Google Colab. Everything fits here. So the fact that the cloud storage makes everything easy. So when we're dealing with these data sets, we are dealing with thousands of images, like I mentioned, and it can be a pain to handle that amount of data on your local machine. So having cloud storage to do this is probably the best solution around right now. Also, data privacy. So at least here in Siemens, we have some strict guidelines to deal with data privacy, and we need we have some compliance guidelines to follow. And in the AWS, and I mentioned the other cloud services as well, it's easy, or all of this is taken care of for you. Then we have the elastic computing instances, which are like the virtual machines, or the machines that you use to either train or run the detection of your models. And here you can basically choose like some GPU optimized instances or more CPU oriented ones, and you can adjust it to your computing needs. So for example, for training the model, I'm currently using one of these GPU optimized instances. And then for tracking, I'm using a more CPU optimized. And you can choose like different powerful, less or more powerful machines according to what you need, which is great. It's very elastic. So in the end, we are able to get the results faster, both for training and for tracking when we are using these cloud services, or at least faster than you use on your like working computer. At least mine isn't that good. So now let's focus here on the tracking part of these projects. So now we have our detections, but then we also need to track these vehicles and pedestrians in order to get their trajectory across the videos. To do this, I've been using the simple online real-time tracking algorithm, or SORT, and it's actually a mix of two other methods. One of them is the Kalman filter, which uses the position of the bounding box and this velocity vector across different frames or consecutive frames to predict where the object is more likely to be next. And the Hungarian algorithm, which checks the overlap, so again, the intersection over union between the bounding box in consecutive frames. And then with information from both of these methods, we are able to basically give the same ID to the same object or vehicle in this case across the different frames of the video. And now, since we're dealing with video, right, we can do some additional pre-processing. And in the case of Traffic Airnalytics, we really need to do this. So one of the things that we can do first is just adjust video properties like the frames per second, the time frame, like cropping the image if you want to exclude something. Then I have here a video to show you what I have to do here. So we want to mark down the entries of interest here in green, the exits of interest when we're dealing here with a roundabout or intersection. And you can also like mark some regions of no interest, so regions where you don't want to see any sort of detection. And then another cool thing is, well, we are acquiring images with a drone that can move from time to time. So something we do in this project is we check for large drone movement, and if it happens, then we are asked to redraw the entries and exits so they are adjusted to that new position of the drone. So finally, you can see here a small example of our results. You can see that most of the vehicles are being detected here. They're being tracked, so they're being given the same ID throughout the different frames of the video. We can also then check when one vehicle crosses one of the entries or exits that we marked here in the roundabout by checking the intersection of this like instant trajectory with that each entry and exit. And then we can perform some analytics like you see here, where we are just counting the number of vehicles that go through each entry or exit and the class as well. And also we can check for each ID what was the route that it took. So in which entry the vehicle entered and what exit did it take. And then we can do some analysis in order to see what are the preferred and also least preferred routes in a roundabout. So here, maybe for simplicity, we can also sort of merge together these small exits and entries. And you can see here, for example, that entry 1 and exit 4 was the preferred route in this video sample. Then all of this data that we get on traffic flow can be used as an input for simulation software like you see here, that is then used by our traffic engineer colleagues. So basically, they use this sort of software to sort of play around with the traffic signals, the traffic lights. They can also change the time that the traffic lights change from red to green. Um, they can also sort of replace this intersection with other road configurations, like, as I mentioned, the roundabouts or vice versa, right? And they do all of this trying to find the best traffic solution. So far, I've been talking about mostly this traffic analytics project, right, where we perform the vehicle detection and tracking in these drone acquired video streams. But then we've got our colleagues at the mobility department came with us with this new project proposal called 5G Mobix. And 5G Mobix focus on traffic safety assessment. And we try to calculate some safety metrics in interactions between vehicles and also between vehicles and pedestrians. So one of the first steps or one of the new things in this project compared to the traffic analytics one is the pedestrian detection that we didn't have before. So this was actually that requirement that I mentioned before of those new classes. It came from this project. Then the second like different thing that we really needed to do for this project was also to get speed and distance measurements from the video, which was something that we weren't doing before. So now also to give you like a bit of information regarding how these projects came to be. So in 5G Mobix, we are focusing on autonomous vehicles. So autonomous vehicles are a part of the future of mobility, as you know. And although there is a lot of buzz around this topic, we are still some years far away from seeing them on our streets and as part of our day-to-day lives. And there has been like a race not only for technology in this field, but also to try to find the most trustworthy and safe car. And another thing is that not only companies are investing in research and development in this field, but also countries. And actually, the European Union has like several ongoing projects on this topic to understand what are the best technologies that will support this new wave of mobility. So self-driving cars don't exist by themselves. They need roadside infrastructure, guidance, and also communication systems. So this 5G Mobix is actually an European project that aims to showcase the added value of 5G technology for this connected autonomous mobility. Its goal is to bring automated driving to the next level of automation, and it focuses on this cross-border environment. So there is this network handover between countries, and this must be studied so that autonomous vehicles can go safely from one country to another. And as you can imagine, in the European Union, this is an important factor to be considered. So this project covers actually 10 countries from the European Union, and then also Turkey, China, and South Korea. It involves 30 network points with 5G nodes, 24 automated vehicles of different types, like cars and shuttles and others. And it covers 5 use cases that are all focused on these cross-border operations. So in Siemens Mobility's participation in this European project, the goal is to evaluate 2 use cases on highways and another use case in a cross-border urban environment between Portugal and Spain. So the traffic scenarios that we'll be considering in this project are the overtaking or automated overtaking scenario, where basically an autonomous vehicle will perform an overtaking maneuver, and this will be happening on a highway. And some of these other vehicles that we see here are connected to the 5G network, but there are some that aren't. And we'll also be evaluating how safely this maneuver happens. Then we have the lane merge scenario where the autonomous vehicle will perform this lane merge maneuver onto a highway in those same conditions as before. So some cars are connected to the network, some of them aren't. And there will also be this detection system with some radars and cameras that is connected to this roadside unit, which will communicate with the autonomous vehicle to share the position of those vehicles that aren't connected, so he doesn't get the information like directly from. Then finally, the third and last use case, we will be measuring this interaction between the autonomous shuttle and a vulnerable road user. So basically, there will be a pedestrian crossing the road in front of this autonomous shuttle. And the pedestrians here will be connected through an app that sends their location directly to the autonomous, like to the 5G network, and also an additional pedestrian detection system that will be connected to a roadside unit. So in the end, we are interested in measuring three safety metrics, or these time-based indicators of traffic safety. One of them is time to collision, which is actually one of the most frequently used. So many driving assistants and car collision avoidance systems use it. And it basically evaluates the time to collision in case the vehicles keep their current speed and also trajectory. And we only calculate it if the speed of the following vehicle is larger than the speed of the leading vehicle, which is what is really a risk for collision. Then we're also interested in the post-encroachment time, which is a time difference between a vehicle or pedestrian leaving an area of potential collision and the conflicting vehicle entering it. So in this example here, and what we'll be doing, which is with a pedestrian crossing the crosswalk, it will be the time between the pedestrian reaching the other side of the road and the autonomous vehicle entering the crosswalk area. The last indicator is called time headway, which is the time between two successive vehicles passing the same region on the road. So here we can see Valença, which is this Portuguese city on the border with Spain, where there is actually this bridge that is connecting both countries. And this will be the location where the use case with the autonomous shuttle and the pedestrians will be performed. The trials were supposed to happen earlier, but due to the COVID situation, it kept getting postponed, and they will only be acquiring these videos in September 2021. So the videos will also be acquired with the drone, and will basically be reusing what we were already using for the Traffic Airnalytics project regarding the model for detection. So throughout the presentation so far, we've already covered like the detection part and also the trajectory part of these projects, right? But now we'll have to talk about deriving distance, time, and speed from the videos. And then we'll have all the necessary building blocks to calculate those safety metrics that I've explained. So the video is acquired with a drone like this, with a mounted digital camera. But how do we go from digital pixels in a video to a real-life distance in meters? So we need the ground sampling distance, or GSD, which is basically this conversion factor between pixels and meters. And to calculate it, we need the dimensions of the camera sensor, and this is something that you can get like from the specs when you buy any like video recorder or a camera. Then you also need the dimensions of the captured video in pixels and the altitude of the drone. And these are the three informations that you need in order to calculate the GSD. So from the ground sampling distance, we can derive the real life distance in meters. knowing the frames per second of the video or the frame rate at which the video is acquired, we can derive time, like the time that goes through every 2 consecutive frames. And by dividing distance per time, we are able to get the speed values. So finally, I have here a sample of the results that we get with the 5G Mobix project. And well, I mentioned that the actual videos of the autonomous vehicles will only be acquired in September this year, so I still don't have them. But we've already started developing this solution using some sample videos from the Traffic Airnalytics project. So far, we have already calculated the time to collision and also the time headway. So the PET we haven't calculated yet. So here in this video, you can see the vehicles getting detected and then getting detected. You can also see that the speed is being calculated here frame by frame. And then you can also see the time to collision here being calculated between car 41 and 40. And in this instant here, it's actually 1.8 seconds. And here it's being calculated because they are still more or less on the same path. So I mentioned that the trajectory needs to be the same for this indicator to be calculated. So then, as soon as the leading vehicle makes the turn, so they are no longer on the same trajectory path. And also you notice that there was a bit of an angle between them, but we have like a little threshold there of around 10% of the angle to still consider it to be the same path. But as soon as it turns, then we stop calculating time to collision between these vehicles, and then we start calculating it again for these 2 vehicles here, while the following vehicle has a larger speed than the leading vehicle, which is another constraint for the safety indicator, like I mentioned before. And we can see it here being calculated until both vehicles stop. In this clip, there are actually no unsafe situations, since this time to collision threshold for an unsafe situation is of 1 second, and here we always have over 1 second of TTC. Then in the time headway, so as I mentioned, this is the time between 2 vehicles passing the same region on the road. And here you can see we've marked this region as a red line here using OpenCV. And you can see here as car 33 and car 34 pass that line, we can see here the time headway between them being calculated, and we actually were able to find a sample of an unsafe situation. So probably the following vehicle was being not as careful as it should. Because the threshold here is of 2 seconds, and what we find here is it's being calculated at 1.67 seconds. And then, as this car 36 passes the same region, we are back to a safe driving situation. So I just wanted to leave you with some key takeaways from this presentation. I will start with listen. So data is everything. You should iteratively improve your data set and model. And I know this is cliche, like for every data science project, right? But I think it's really important to have very different images to train on with different characteristics, like lighting, the contrast, the rotation. And if your data set doesn't have that by itself, then you should use data augmentation or other techniques to artificially generate that diversity that you really need. And you could also try to fine-tune your model, and all of this will play a really big role in improving your results in the end. Then, computer vision is an ever-evolving field, so keep up with it. So here I have a very clear example of how true this is. So when I first started working on these projects, I was using YOLO v3, but then in April 2020, YOLO v4 came out, and it said the paper says it has an increase of 10% on both like accuracy and speed. And I decided to try it out, and the improvement on the results was really noticeable. So yeah, you need to keep up with these new developments in the field, and you shouldn't be afraid to try out these new things. Then you should also evaluate the cost benefit of potential solutions to your problems. This also sounds cliche, but I'll explain a little bit what I mean here. So sometimes when you're trying to answer your computer vision problem itself, maybe there is already like an API that can solve your problem easily. So do you really need a more customized approach? So this is something that you need to ask yourself and explore what is already out there to see if you should really like create a custom solution to that particular problem. Another thing here can be like the labeling solutions that I mentioned. So maybe it could be better to use some crowdsourcing, because even though it has costs, I mean, labeling data yourself takes up a lot of time, and so that could be an investment and could free you up to do other tasks, of course. And also the cloud option. So it obviously has some associated costs, but it can save you a lot of effort. So you basically need to analyze your problem and all its different perspectives as well, and the limits that you have when you're trying to solve all of your potential problems within it. And then a final conclusion here, inter-organizational collaboration goes a long way. So when we launched that labeling contest at Siemens, I was worried about participation, since, I mean, it's a really boring task, right, to like draw those rectangles. But in the end, we had some very active participants that helped out, and we ended up getting a very good data set. So leveraging your company's strengths can have some great results. And yeah, this is what I have for this part of the presentation and the workshop. So now I think we can open the field for some questions. Let me
Hello.
see here.
Yeah, well, I'm also back to help you a bit with the questions.
There are no questions, are there?
Yeah, certainly no questions, but maybe I can ask one relevant question. It's that, and I think it's really relevant for the participant. So let's say if you would have 1 week to explore a computer vision challenge, so that's very limited in time with a data set, but with a data set and even some labeled also images. And in this case, it's a detection problem, just a detection problem. How would you go about it, or what advice would you give to the participants to go about this, or some kind of approach, for example, here?
Okay, yeah, okay. So depending on your problem, but I'm guessing it's like a standard object detection problem. I guess you can probably just try to find online some pre-trained weights of any model that you want to use, download them, and apply them directly. So you don't need all of these things that I talked about training your own model. You can basically skip that and just use some pre-trained weights. That would be like a major time-saving thing to do.
Mm-hmm. And how would you, if you would go around fine-tuning the model? So, for example, for at least from my knowledge, it's that how a lot of computer vision problems get solved is that you take a more general model. So let's say YOLO, for example, and then you can use a really small amount of images to fine-tune, so to say, the weights towards the goal that you want to do. Mm-hmm. Do you have any tips or tricks on how to do best this approach, or anything that you'd like to leave to the participants when they're going to be doing that?
Yeah, so I mean, you always need to find like documentation on how to do that with the neural network that you're using. But I mean, generally speaking, you basically need to freeze the initial layers of the neural network that you're going to be using, and then you're basically just training the final layers. So those layers that are responsible for extracting like more object-specific features. like high-level features. And then, yes, one of the benefits of using that approach is that you can have like a smaller data set just to fine-tune the results towards that different class or something that you want to train on.
Mm-hmm. And then one final question, maybe it's what is the impact of the quality of the pictures and the end results? So because life is not always perfect and you cannot have a full HD camera everywhere you go. So how do you see the impact there?
Yeah, well, yeah, the impact is noticeable. So it all depends on the data that you use for training. So, for example, I showed an image there of a roundabout that had an area that was with shadow. So I really faced that issue there. It was very hard to get detections on like lower contrast areas of an image. But what you can do there is maybe like perform some data augmentation where you mess around with the contrast of the training images, trying to reduce it so that the model learns to identify those objects even in those like bad quality images in the end. And I mean, I'm talking about contrast, but also like blurred images or videos. Yeah, it could also be a solution.
Perfect. Yeah, I think the data augmentations can help a lot in different cases. That's also at least from what I've seen. And maybe for you, what do you think from your point of view, it's the most difficult things when you're working or the most difficult aspect of working in computer vision?
Okay, so
Besides the lack of data in labeling, I think that's an obvious one.
Yeah, well, I think for me, like one of the main challenges was to always validate the data, because at least for me or for this use case, I had to use a lot of data sets that were a bit niche. So they weren't very validated before, and I noticed, and also, yeah, this is also a warning for the participants here, is that you shouldn't really trust every data set that you find online. um, uh, Even these imaging data sets, they can have a lot of issues with the labels. And yeah, it was the case here. And I had to basically go through like thousands of images, just checking if everything was okay, which was a pain. But in the end, I mean, you see the results and you get really happy, and you think that the hard work paid off. So
Perfect. Well, thank you so much. I think now we have a small practical part as well prepared for us.
yes, indeed.
Okay.
I'll
All right. Then
share.
I'm going to hide myself and good luck.
Okay, thank you. Okay. Oh, just a second. Okay, so just so you know, I think that this folder has already been shared with you. So it has like the PowerPoint that I just showed. It has this Jupyter notebook, and then it has this sort module here, some inputs, and also some YOLO related files that I'll go through in a little bit. So starting here with the notebook. So I've prepared this little task for you to do some things that I talked about during this presentation. So the goal of this notebook and this task here is to basically count the number of vehicles that go through each of two routes on a highway. So I will show you the input video just here. It's this highway.mp4. Okay. So you can see here you have some cars that are going like upwards, so let's call that north, and some cars that are going this way, so let's call that south. And it's just like a short video, 1 minute, and this is what we'll be analyzing in the end. So, okay. Okay, so as you could see in that video, we are dealing with this static camera that is at an eye level perspective. And the code that I've put here was actually developed within the Traffic Airnalytics project, because one of the requests of the customer was to also expand the project towards this static camera video analytics, which is like a simpler project or version of the project. So the input video that I showed is free to use, and I downloaded it from this website that you see here. The detection part of the notebook was adjusted from these OpenCV code samples for object detection, so I'll just show you here. So OpenCV has these sample codes with this DNN package within OpenCV, and it was taken from here. And then YOLO v4, so we'll be using some pre-trained weights trained on the COCO dataset. And I got these weights from the Git repository. You can also check out their paper here. I put all of these links here. And also the sort module, so for object tracking, you also have the Git repository here. So to start off, you obviously will have to install the required packages before importing them. And generally, you can just use the most recent stable versions available via pip or conda. But for OpenCV, you can't. You need to install the 4.4.0 version. And I recommend, for simplicity's sake, because installing OpenCV can be a pain, to use the Conda Forge version and use it and install it for your Python version. So something like this, like 3.7.2 in this case. So then we import here some of these packages that we'll need. And then you'll be defining some input parameters. So the model, which is the weights of the model, which are stored as YOLOv4.weights in that folder that I showed before here. So then you'll have to adjust this to your own paths if you want. The weights file is here. Then you also will need the configuration file, so the actual network configuration that we'll be using. So for YOLO v4, which is this .config. The classes file, which in this namespace where these weights were trained on the COCO dataset, it has this coco.names name, the file, which is also here. And then the framework is Darknet because that's the name of the framework of YOLO that YOLO uses. The backend and the target, we are just using the default ones from the detection samples from OpenCV. Then the confidence threshold that I also mentioned in the presentation that we'll be using is 0.5. The non-maximum suppression threshold is 0.4. And here the max age and minimum hits are some parameters that we'll need for the tracking part of this task. So first, maybe I'll run this slide for you, although I have already the results here. So let's load the classes names. So we are basically just going through what is within that coco.names file that I showed you. And you can see that there are a total of 80 different classes identified in the COCO dataset. So it goes from like person, bicycle, car, motorbike, to like food, like pizza, donut, cake, or some things that you can find around the house, like, fork, knife, microwave, stuff like that. So there's a lot of classes in this dataset. So now we can load the convolutional neural network. So to do this, we use OpenCV DNN to read the network, and then we pass it the model, so the weights, the configuration, and the framework that we'll be using. We also set the backend and the target with those default values that we determined there. And here we get the names of the output layers of YOLO. And in this case, YOLO v4 has 3 output layers, and this is because it outputs detections at 3 different scales, making it more sensitive to like smaller objects detections, which was also one of the reasons why we chose YOLO v4 for our projects here with with the small vehicles, right, in the drone images. And then moving on to the first example that I have here, which is just object detection. So first we define this draw prediction function, which will draw the predicted bounding boxes with an associated label for class and also the confidence score. So we can see here we are using the OpenCV like draw rectangle function, which uses, as I mentioned in the presentation, also the top left corner and the bottom right corner to draw the rectangle. We'll be showing the confidence with as a float with 2 decimal points. And then the label will basically be the class. So one of those things like person, bicycle, or something like that. And then the confidence score like 0.85, for example. And that's what this function will do. Then the post-processing function will filter the detections over the confidence threshold that we defined above as 0.5. It will also apply that non-maxima suppression in order to get just that optimal bounding box, like I showed you in that example with Audrey Hepburn. And it will finally draw the predicted bounding boxes using the function that I showed before. So here we're just initializing some variables. We are getting the frame height and width from the image itself. And then we will be cycling through the outputs from the 3 output layers that we have. And we're going through each of those potential bounding boxes that we have there, like that huge dense array of bounding boxes that YOLO provides. So here, basically, the detection will have each box's coordinates. So those are the first 4 points, and then from the fifth point onwards, we will have like the scores per class. So in this case, since we are considering 8 classes, this detection vector will actually have 84 84 elements, basically. So 80 for scoring the different classes and the bounding box coordinates. So we'll get the scores, we'll get the class ID by determining the index of the largest score that we have. So we'll get what class we have identified in that detection. And we'll get the confidence as the score pertaining to that class. And then we'll only be keeping the detections where the confidence will be over that confidence threshold that we defined above, so 0.5. We'll be getting the centroid information here. Remember that in YOLO, everything is normalized to the size of the image. So here we multiply it to get the actual values by the frame width and height. These are the bounding boxes, like width, height, the left side and top of each bounding box. And then we'll save the class index, the confidence, and the bounding boxes coordinates. Then after we remove, so basically here we are already considering just those boxes that are above the confidence threshold, we apply the non-maxima suppression. So by this stage we'll only have like Audrey Hepburn's face before with just those very good detections, but still like 3 or actually 9 in YOLO bounding boxes around it. And so we apply non-maxima suppression here, so we can get just 1 detection per box, per object. So, okay, then we basically draw the surviving bounding boxes using the draw prediction function. So let's do this, and we'll now be applying this to an image, a sample image that I found of like a scenery here in Lisbon. So here we are basically loading that image, so I can show you that input here. Okay, So you can see here there are some people on the street, some cars, and this tram, this electrical tram that we have in Lisbon. And so we are basically using OpenCV to read this image. Then we need to create this four-dimensional blob from that image, which will be used as an input for our neural network. And what we need to pass here is the image. This is a scale factor, and this is the size that the image will have when entering the neural network. So what you should do here is use the input size of the neural network here. So to do this, you can check like the config file itself if you want. So here in the beginning, oops, sorry. So here in the beginning, you have the width and height of the input layer of the neural network, and you can use these values there. Then this swap RB flag is just because when you're reading images with OpenCV, it swaps the red and blue channels. So instead of RGB, it is BRG that OpenCV uses. And that's it. So then you set this blob as the input for the neural network, and then you run a forward pass to compute the output of the layers listed in outname, so those three output layers that we have. And then you apply that post-processing function to those outputs. So you'll be going through all of the detections that YOLO has generated and then performing those cleaning stages that I mentioned before. And finally, we can see the results. Enough talking. And you can see here, actually the tram gets identified as a train, but you can see the person, car, and so on, the fire hydrant being identified here. Let me just run this again. Okay. Something that, okay, sorry, I had made some changes up there for this to be more readable. So you can see that mostly every object that you see here gets identified, but there are still some issues like with occlusion. So if you see here, there is this little dog that didn't get identified by the neural network, and this could be because there is this pillar here obstructing the view of it. And you can also see then the confidence score. So pretty high generally, like the car is almost 100% sure that that is indeed a car. And yeah, okay, moving. So now we will be doing the exact same thing, but I will be feeding to this model the Airnalytics example picture. So let me show you what it is. So you can see here, it's like one of those images acquired with the drone, right, of a roundabout and the vehicles. And these are the results that we get. So basically, almost nothing gets detected. Some of these cars are actually being detected as cell phones. And this one here, maybe because it has like a more sideways perspective, it's getting detected as a car. So bad results all around. And also, I mean, if you consider like a usual picture that you take from this distance at an eye level, then yeah, something black and square and small will probably be a cell phone. So you sort of understand the reasoning behind this, right? But in this case, it's not applicable. And now, well, since we don't really, at least for this problem, we aren't interested in detecting cell phones or anything like that, we can also filter out the classes that we are interested in this task here. So car, motorbike, bus, and truck, which are the four vehicles that we have in the 80 classes of the COCO dataset. Then we can also start by loading the video and extracting some information from it. So OpenCV also has these cool handlers for video, so video capture. And we can extract some properties like the frame count, the frames per second, the frame width, and frame height. And we can get the duration by dividing the number of frames by the frames per second. We get the length of the video. So the duration of the video is 1 minute. There are 1,800 total frames. It runs at 30 frames per second, and it has these dimensions, so it's pretty much a 4K video. Then, since we know already that this video has some large dimensions, here I just made a small update to the labels to make them larger so that you can actually see them. And also, I've updated this post-processing function to only draw the selected classes. So pretty much all of the code that you're seeing here is the same as before. But here, when we are drawing the surviving bounding boxes after the non-maximum suppression and the confidence threshold, we'll just be filtering the ones that are within the selected classes that we considered before. So now, we'll be applying that post-processing function to some sample frames of the video. And here we just want to be able to see here in the notebook like a small sample of the frame. So I'm going to do this between frame 175 and 178. The frame index will start it out at the start frame, so 175. And we'll start processing the video frame. So we grab the first video frame, so frame 175. We get its height and width. We create a blob from that frame in particular. We do the same things that we did before for those images. So these are the inputs that this blob will have. Then we set the input again, we do that forward pass, and we have our outputs for these 3 frames. So just a small sample that I'm showing here within the notebook. So as you can see, all the vehicles get detected, which is great. These 2 are being marked as trucks. Here you could also have that discussion if this is a van or a truck, or that's another topic. But yeah, everything is getting detected with very high confidence rates, which is great, and for all frames. So moving on. So we are able to basically detect the objects, know their class and the confidence for each class, right? So now we want to track them. So now I'll be updating this. You had a lot of ways to do this, but I'll be using basically the same post-processing function, but instead of in the end drawing the detection, so using that drawPred function, I'll actually be updating this tracker, which is a sort object. So basically, we perform that confidence threshold, the non-maximum suppression, and then for those, and also the classes selection, right? And then for those detections left, we will update our tracker. And this is the tracking part, or the important part related to tracking here. So let's see how this all works, right? So again, I'll just be considering some frames of the video. We here initialize this memory dictionary that I'll get into a little bit. And then we also have these colors, like a list of different RGB values that we'll be using just to give different colors to the different tracked objects. So here we initialize the tracker. And this tracker object is going to be created before we loop over the frames. And it will get updated every frame in that post-process tracking call. So here we call this tracker.update, and that is what will update the tracker with the tracking for every new frame that we process. So here, the input parameters that we have is this max age and min hit. And the max age is basically like the number of frames where the ID is saved when there is no detection, right? And the minimum hits is the minimum values of a hit streak of a heat sink, so it gets displayed in the outputs. So we set this value at 5 and this value at 1 because we are performing an analysis on the tracking for every frame. So we always want to output these sorting values. So then we start processing the frames of the video like we did before. We do the forward pass within the network. Then we get the tracks, and here the tracks are basically, so the output of our post processing at this point in time is actually the bounding box coordinates and also a unique ID for each object that was successfully tracked. So basically, yeah, that's what you see here. So for each track here, we are actually extracting the bounding box coordinates and then also the ID. And then we add that track to the memory dictionary so that in the next frame iteration, we will know what objects we were already tracking, basically. Then we here, for each successfully tracked object, we pick a color. So that color will be constant for each ID, which is what we want. So you always see the same color when we're tracking along the video. We'll be drawing the bounding box. We'll be printing a label that now won't have the confidence, but will be showing that unique ID, proving that we are tracking that object that we want. And this is just outputting that to the image. And then, sorry. Okay. Can you hear me? Okay, I think I had some connection issue, but I'm hoping it's okay now.
We can hear you,
Okay,
but I don't see your screen anymore.
Okay, great. Thank you. Really? No. Okay, let me share again. Okay. Okay, can you see it now?
Yeah.
Okay, great. Thank you. Sorry.
No
okay.
worries.
Okay, so when we have successfully tracked an object throughout the video, it means that it was tracked in the previous frame, right? We were able to track it in the previous frame. And so we can get the bounding box that object had in the previous frame. We can get the centroid that it had in the previous frame. And we know the centroid that this object has in the current frame. And by drawing this arrow between them, we kind of have that instant trajectory that I showed you also in those examples in the PowerPoint presentation. And we can draw this using this arrowed line, just so it looks cool. It's a little arrow. And now, yeah, we can see these outputs for this like sample of 3 frames, I think, that I have here. Okay. Okay, so you can see here, so each vehicle that we have here has a unique ID, so different from the others. You can also see that between frames, the same object remains with the same ID, which is what we wanted, right? And also, well, this is just for looks, but the bounding box also has the same color across frames. And you can also see like the small arrow indicating the instant trajectory over here. So all of that is working fine. Now the final thing that we want is to count the objects and identify the routes. So here I'll just be defining some auxiliary functions to determine like the intersection. So when the arrow line will intersect the entry or exit, in this case, we'll just have a line over here for cars that are going in this direction and another line over here for cars that are going south, so to speak. And also determining just the midpoint of a segment, a line segment. So here, the code is basically a repetition of what we had above again. But now we'll be also storing some information for every frame. So we'll be storing it in this intersect data frame with the frame, time, route, and ID. And this will be updated every time a vehicle crosses that north or south line. We'll also have a counter here for those intersections, so north and south. And here, maybe something that I wasn't doing before, I'm saving the time. So again, just by dividing the frame index by the frames per second, we can get how much time has passed in the video up until this moment. And we're just saving the time with like 00.00 dots 00 seconds, in that type of format here. Then again, we perform that for pass. Here we are now drawing the lines of interest for counting and for route identification. So we need like the start of the line and the end of the line for the north route, it will be something like this. And for the south route, which will be something like this. So here we have those coordinates just declared here. The north line will have an N printed on the middle of that line segment, and the south line will have an S. So again, we'll perform the tracking. But here, the new thing is that we'll be checking for those intersections. So if there is an intersect between that arrowed line, so basically the line between the centroid in the previous frame and the centroid in the current frame, and one of the lines, then we'll increase the counter and save which ID crossed that line. And that's it, basically. So then we'll also be printing on each frame the counter, so the number of vehicles that go through the north and south lines, and also the time. And we'll update this data frame with that information as well. Now let's look at the results. So here we'll be running this for some more frames, because I wanted you to see like some vehicles obviously crossing the lines. So here you can see the north and south lines, the vehicles being tracked. You can see here already that one vehicle crossed the north line, so the counter increased here. And some time later, another vehicle crosses it, so the counter increases there, and so on and so forth, also for the south line. And finally, the data frame will be storing information like this. So the frame, time, route, and ID of the vehicle that crossed that line at that time. Then we can output these results for the whole video. And here the code will again be pretty much the same as in the previous step, but we'll need this writer. So this is basically to save each frame as a new video file. And here in the end, you just need to do this. So basically, you are writing each frame to this output video MP4 file that you also have in that folder that was shared with you. But you can also run this again if you want, just to make some changes or export the code, anything you want. And we'll also be saving that data frame to this root CSV. Now we can do some results analysis, like some random things that I thought about for this particular problem. So which route has more traffic? We can perform some counts here to see. So 100 vehicles crossed the north route and 108 crossed the south route. Then we can also see here like a little plot showing so that the preferred route was actually the south one with the number of vehicles. Then we can also try to investigate how does traffic vary over time. And to do this, we can create like this group by here of that intersection, the F that we have. And you can see here that there are some seconds of the video that have basically no counts, meaning that no vehicle crossed the line in that second. So just so that the graph looks pretty in the end, we can just fill out those missing values with zeros, which is what we are doing here. And then finally, we can plot something like this, where you see the traffic evolution per route. So the south in red and the north in green, and the number of vehicles that went through during this minute of video. Of course, this isn't very interesting with such a short video, but imagine if you have like hours of this, it could be an interesting find to see when the traffic flow is really worse. And yeah, this is what I had to show you here in the practical part of the workshop. If you have any questions, I think that you can like reach out to me via LinkedIn or something. Yeah. But also, if you have any questions right now, you can also, I think, post them here in the chat. Let me see if there is any.
No, I don't think so.
Okay.
But as usual, I can maybe ask one question. I know that also sometimes debugging these models is a bit of a hassle. And do you have any practical tips that what people can do when they're debugging and when something doesn't look right, for example, and what to look out for?
So you mean when debugging, like, I mean, in this practical part, so when you're dealing with the detections and the tracking? Okay. Well, it's always important to, to break down the code. So yeah, I mean, this is kind of a simple example, and it sort of got a bit complex, or there's a lot of lines of code here, right? But it's always important to like look at certain frames of the video to try to investigate what's going on, or if there's anything going wrong there. Yeah, I mean, it's like a usual debugging tip, but yeah, break down the code, split everything into little pieces, and try to find out what's going wrong there. That's my advice, I guess.
Okay. And is there anything that you would have liked somebody told you a year ago on any kind of mistakes or error that you made, and you would have liked to known that you know now?
Yeah, I mean, there's a lot. This has been like a very enriching experience to be working on these computer vision projects. Yeah, I mean, most of the advice that I can give there is mostly related to the data quality. Again, I'm always talking about that, but yeah, the impact, the things that I talked about during the presentation. So pay attention to the data, validate everything, because in the end you can spend hours training a model, and then because the data wasn't so good, you end up with like something that you can't really use in the end. So yeah, again, validation is extremely important. Yeah, that's my main takeaway for you, I guess.
Okay, well, thank you so much. I hope this was useful also for the participants. Like I said, they have a challenge, a computer vision challenge during the next 2 weeks. So I hope it will help them, especially the ones experience. Karina, thank you so much for your time and for making yourself available. At least I found it very interesting, and as well also to get to know a bit what work Siemens is doing. So thank you very much.
That's great. Thank you. And I really hope this was useful as well for the participants that will be watching this. Okay.
Perfect. Great.
Thank you. Bye-bye.